So, since this delta naught x is of my choice, I can take delta naught to be xn itself. So, let us take delta naught. The only thing I have to make sure is xn is in di, that means it is invariant. So, take delta naught x is equal to xn. Now, this clearly belongs to di. Why? Because to see that it belongs to di, what you have to check is delta naught of x1 plus c, xn plus c, this should be same as delta naught of x1, x2, xn plus c. But what is the delta naught of x1 plus c, xn plus c? Delta naught of x1, x2, xn was same as the last component. So, delta naught of x1 plus c, xn plus c would be same as last component, which is nothing but xn plus c. But this is the last component of x1, x2, xn, so this is same as delta naught of x1, x2, xn plus c. So, this happens for every x and c belongs to R. So, that is the reason why delta naught belongs to D. So, MRI under square error laws is delta naught x is same as xn, and what is a u star? U star is whatever delta naught you have chosen, which is xn given d is equal to d at theta is equal to 0. So, what I need to find out is what is a conditional PDF of xn given d is equal to d. So, let us try to quickly do that. So, under theta is equal to 0, joint PDF of x1, x2, xn would be how much? It was f of x1 minus theta, x2 minus theta, xn minus theta, where f is PDF corresponding to capital F. It is same as f of x1, x2, xn, where f is a PDF of capital F. In general, it will be f of x1 minus theta, xn minus theta, but I have taken theta to be 0 because I have to find all these conditional expectations under theta is equal to 0. So, first to find the conditional PDF, now you know that conditional PDF is always proportional to the joint PDF. So, f of xn, let me just find it out what is a joint conditional PDF. So, what is a f of d1, d2, dn minus 1, and let us say xn at the point d1, d2, dn minus 1. So, what are the transformation I have to make at the point when xn is fixed at t? So, what transformation I have to make? In this x1 was x1, xn was xn, so I have to make d1 minus xn I am putting here as t. So, what you have to do is you know the PDF of x1, x2, xn at the point small x1, x2, xn. What you have to find? You have to find the PDF of d1, d2, dn minus 1 at the point d1, d2, dn minus 1 t. So, the transformation which you have to make is d1 is same as x1 minus xn, and here xn has been fixed at t. So, d1 minus t, d2 as x2 minus t, dn minus 1 is same as xn minus 1 minus t, and t is same as xn. So, if you want, first you can put here d1 as x1 minus xn, d2 as x2 minus xn, that is those are the transformations, and d minus 1 is nothing but xn minus 1 minus xn, and t is same as xn. So, let us try to see what is a Jacobian, and so your x1 becomes d1 plus t, x2 is d2 plus t, xn minus 1 is dn minus 1 plus t, and xn is same as t. Now it's a linear transformation. You can see easily that Jacobian is always 1. It would be a triangular matrix. Del x1 by del d1 is 1, then the last with respect to t would be 1. So 1, 0, 0, 0, 1. Del x2 by del 1 is 0, del x2 by del d1 is 0, del x2 by del d2 is 0. So now 0, 1, 0, 0, 0 in the last one, and so on. So Jacobian would always be 1. So what is the joint PDF of d1, d2, dn minus 1, xn at the point d1, d2, dn minus 1 and t. So Jacobian is 1. I have to just make the transformation of x1 as d1 plus t, dn minus 1 plus t, and t minus infinity less than di less than infinity, r I is equal to 1 t. What I have to do is, to calculate this, I have to find expected value of xn given d is equal to d. Actually, I should write down not d is equal to d here, because d is a random variable. I can just put this. Okay, so let's try to find out what is expected value of xn given d is equal to small d. That is what I have to do. So for that, I need to find out what is a conditional PDF of xn given d is equal to d. So f of xn given d is equal to xn at the point t when d is given to be d. So this is a conditional PDF of xn at the point t when d is given to be t. So this is same as joint of xn and d, which is basically this. Divided by marginal of t. Marginal of d means in the joint you integrate out the unwanted variable, which is t. So minus infinity to infinity f of d1 plus t dn minus 1 plus t. So this is what the conditional PDF is. Now if conditional PDF is this, I can find out the MRIE. So let us try to see what is MRIE. Star x, which is nothing but xn minus E theta is equal to 0, xn given d. So this is same as xn minus expected value of this PDF. This PDF is in R, and it would be a function of t. So this is same as, and this is a constant because here t has been integrated out. So this will be constant. So this would be nothing but minus infinity to infinity x to xn. So this same as t f of xn given d at the point t given d dt. So what is that? This is nothing but xn minus infinity to infinity t times this quantity, except that my small d here is capital D was fixed at small d. Here I am writing down everything in terms of a random variable only. So I have to replace this d by di's. So f of d1 plus t dn minus 1 plus t t divided by minus infinity to infinity you see, note that here, if you want, you can write down this as some other variable, because this has to be integrated out. So if it is integrated out, you can put any variable over here. You can make the transformation t is equal to u. So this is, that is done just to avoid this dt with this dt. All right. Now with this, With this, I can write down this as xn minus, there is no t over here, so this is kind of a constant, so this goes 1 upon that, which is equivalent to saying that this is same as minus infinity to infinity t times f of d1 plus t dn minus 1 plus t. Yeah. Okay, it's not visible, so let me write down a little bit below. So this is same as xn minus infinity to infinity t times f of d1 plus t dn minus 1 plus t t dt divided by minus infinity to infinity of this quantity. Now again I can replace u by t. So this is same as f of d1 plus t dn minus 1 plus t t dt. Now dn's I know are nothing but minus infinity to infinity t f of x1 minus xn plus t xn minus 1 minus xn plus t t dt divided by minus infinity to infinity f of x1 minus xn. I'm just doing simple algebra, trying to simplify this integral. Minus xn plus t, because dn minus 1 is xn minus 1 minus xn plus t. So in general, what I've done is I have replaced di by xi minus xn over here. Now what I do is in the integrals over here, I make the transformation xn minus t as t prime or u or whatever, and then I replace again that u by t. So I make the transformation xn minus t as u, this becomes xn minus infinity to infinity. Jacobian everything would be 1, so t is nothing but xn minus u. F of. Now this minus, all these xn minus t's have become u, so this becomes x1 minus u, xn minus 1 minus u, xn minus 1 minus u, and then t is nothing but xn minus u. Divided by minus infinity to infinity f of x1 minus u, xn minus 1 minus u. So you can bring this over here. This factor is same, so it will be xn minus u, so which will become only minus infinity to infinity u x1 minus u divided by So this was derivation for the situation where you have a squared error loss function. So we have proved the first result, which was for general loss function W. So MRE is nothing but delta naught x minus u star d, where u star minimizes expected value of W of delta naught x minus c given d is equal to d. And this minimizer is unique if your loss function W is strictly convex. So now we are in a position to write down our general result, which let me do it over here. So let us say this is the theorem. So delta naught is a given invariant estimator. This I can choose as per my choice. The only thing I have to make sure is its risk is finite. With r delta naught theta is equal to 0 is finite, because risk of this would be constant. Suppose that for every d belonging to Rn minus 1, there exists u star d that minimizes psi c, which is expected value under theta is equal to 0 of w of delta naught x minus c given d is equal to d. Over all functions which minimizes this, then what is your MRE? MRE is nothing but delta star x, which is delta naught x minus u star d. And MRE here may not be unique, because there may be more than one minimizer. So MRE is this. Now, second part, we have seen that if W was strictly convex and non-monotone, then the minimizer is unique. So everywhere I am assuming my W is convex and non-monotone, so that the minimizer exists. So here I assume that W is convex and non-monotone. So these are assumptions which we make throughout, because that only guarantees that there will be a minimum. Now, if W is strictly convex, then the MRE in A is unique. Third part says I can find out what under if Wt is t square, that means you are dealing with a convex loss function. In fact, it is a strictly convex loss function. It is non-monotone also, because it is decreasing for t less than 0 and increases for t greater than 0. So its graph, look like Wt is equal to t square is like this, which is non-monotone and convex. So the minimizer would be unique. Then the unique MRIEE is delta star x, which is basically nothing but xn minus E theta is equal to 0 xn given d. That is what we have seen, which is nothing but minus infinity to infinity t times f of x1 minus t xn minus t dt. This is the one which I derived it over here under the square root of function divided by minus infinity to infinity xn minus t dt. Now, the unbiased estimator in C is unique and delta star is unbiased. So all these parts I have already proved. The only part which I need to prove is the unbiased part. So let's try to see what is expected value of under theta of delta star x, which is nothing but expected value of theta under delta star x is nothing but delta n minus expected value of theta is equal to 0, xn given t is equal to t. Which is nothing but same as expected value of xn, e theta at xn, minus e theta is equal to 0 of xn given t is equal to d. So double expectation. Now let us try to see if expectation under theta is equal to 0 has to be changed to expectation under theta. What is the change I have to make? Now I know that if x has distribution function f theta, then x1 minus theta, xn minus theta has the same distribution, except that now theta gets replaced by 0, because probability x1 minus theta less than or equal to t1, xn minus theta less than or equal to tn would be nothing but f of t1 plus theta, t2 plus theta, tn plus theta, which is nothing but f of t1, t2, tn. So which is same as f of t1, t2, tn, which is f0 all t. So what does that mean? So what does that mean is, if expectation under 0 you have to change to expected value under theta is equal to 0, what you do is you replace each xi's by xi minus theta, and then you can put it over here e theta. So this is same as e theta of xn minus e theta. I am changing e theta is equal to 0 to e theta. If I do that, what is, because under E0, x1 minus theta, xn minus theta I have under E0. So that means the same as I change it to E theta, and I replace this each xi is by xi minus theta. So xn is replaced by xn minus theta, that is okay. Capital D was x1 minus xn. But x1 is replaced by x1 minus theta, and xn is replaced by xn minus theta. So D remains the same. Capital D remains the same. So capital D1 remains the same. Capital D2 is nothing but x2 minus xn. So x2 is replaced by x2 minus theta, xn by xn minus theta, theta cancels. So capital D2 also doesn't change. So this is same as capital D doesn't change, is same as small d, because this small d is a fixed quantity. So I am done, almost. So this is same as e theta of xn minus, now it becomes the same e theta over here. So it becomes expectation of a conditional expectation, which I was not able to do over here. I cannot use this as a single expectation because the two expectations are under different distributions. Theta is equal to 0, and here theta, here it is theta, here theta is equal to 0. So this is same as, because it's the same probability distribution, e theta of xn minus theta, which is same as e theta of xn, xn gets cancelled, which is same as theta. And this happens for every theta. So this proves that MRIE under squared error loss function is also unbiased. So let us look at what happens under general loss function. Under general loss function, my MRIE is nothing but this. Delta naught I can choose as per my choice. So that means the only thing I have to choose is U star D. I have to calculate is U star D. But U star D is the one which minimizes this. So which minimizes this conditional expectation. Now note that if this conditional expectation was same as unconditional distribution, my life would be still much simpler. In fact, I'll make my life much simpler. So this suggests if I can choose delta naught x such that delta naught x and D are independent. then I don't have to deal with this conditional expectation. I have to deal with unconditional expectation, and minimizing that could be an easier job. So this suggests that I should choose delta naught x such that delta naught x and d are independent. Now, to exploit this, let us try to recall the Basu's theorem. What does the Basu's theorem say? Basu's theorem says if Tx is complete sufficient, in fact, you only need boundedly complete, but let us write down is complete sufficient. Vx is ancillary. Ancillary means its distribution does not depend on theta, unknown parameter. Then they are independent. So what it suggests? It suggests that if d was ancillary and delta naught x is complete sufficient or even a function of a complete sufficient statistic, then delta naught and d would be independent, and then I don't have to deal with conditional expectation that gets converted into unconditional expectation. So let us try to see whether d is ancillary or not. To see it ancillary, first try to see what is the distribution of x1, x2, xn. This has a distribution function f theta. What I have seen is if x has a distribution function f theta, this implies that x1 minus theta, xn minus theta has the same distribution as f0, right? Just we saw that. You can easily see that probability x1 minus theta less than or equal to t, xn minus theta less than or equal to t, which is same as probability x1 less than or equal to t plus theta up to probability xn less than or equal to t plus theta, which is same as f of t1 plus theta minus theta, f of tn plus theta minus theta, which is same as f of t1, t2, tn. So let me call this as Z1. So what does that mean? The joint distribution of Z1, Z2, Zn does not depend on theta. So this means Z1, Z2, Zn has a distribution which does not depend on theta. So what I need to do? I need to write down this d only in terms of Z1, Z2, Zn. If I am able to do that, if I can write down d in terms of Z1, Z2, Zn, and the distribution of Z1, Z2, Zn does not depend on theta, so that would prove that d1, d2, dn has a distribution which does not depend on theta. So let us try to see what is d1, d2, dn minus 1, which is x1 minus xn, xn minus 1 minus x. But what is x1 from here? x1 is nothing but z1 plus theta. So in general, xi is nothing but zi plus theta. So x1 minus xn would be nothing but z1 plus theta minus zn plus theta. So it would be z1 minus zn. Theta, theta gets cancelled. This is zn minus 1 minus zn. So distribution of d1, d2, dn minus 1 is same as distribution of some function of zi's. But joint distribution of zi's does not depend on theta. So any statistics which is depending on z1, z2, zn will not depend on theta. Its distribution will not depend on theta. So this implies that d1, d2, dn minus 1 is ancillary. So my Basu theorem suggests that I should choose my delta naught such that delta naught is complete sufficient. So if so I can write down this remark now. V is my d is ancillary. Thus, if we choose delta naught such that, so this delta naught is invariant and delta naught is a function of complete sufficient statistic, then MRIE is delta star x is same as delta naught x minus C, because now since the conditional distribution will not depend on D, so this minimizing C will also not depend on this D. So it will be just some constant. So it will be delta naught x minus C star, let me put, where C star minimizes psi C, which is expected value of theta is equal to 0, W of delta naught x minus C. Very simple. So in the situations where complete sufficient statistic exists, and you can find an estimator delta naught which is easy to handle and is a function of a complete sufficient statistic, MRE is very straightforward to find. Just a quick exercise I can give it to you, and then I can conclude my today's lecture. So just see straightforward application of this. X1, x2, xn is IID normal theta 1. So x1, x2, xn has distribution function. So probability x1 less than or equal to t, xn less than or equal to t, they all are independent. So that is same as product I is equal to 1 to n, probability xi less than or equal to t. And probability xi less than or equal to t is nothing but phi of ti minus theta. So this is same as product I is equal to 1 to n, phi of ti minus theta. So it is again of the type f theta, x1, x2, xn, which is f of x1 minus theta, x2 minus theta, xn minus theta. So your f here t1, t2, tn is nothing but product I is equal to 1 to n phi of tn, which is completely known to us. So it is in the setup which we were considering for location invariant series. So my goal is to estimate theta under loss function L theta A, which is A minus theta whole square. So my group of transformations under which this problem is invariant is GC. So this problem is invariant under this group of transformations with corresponding induced group of transformations on parameter space and parametric space as, and action space as g bar c theta is theta plus c, and g c tilde a is same as a plus c. So what I need to do, if I try to look at this, I need to find one invariant statistic which is a function of a complete sufficient statistic, and which is easy to handle. Now in this case, a complete sufficient statistic is x bar. So I can take delta naught to be x bar, because x bar is easy to handle also, because I know the distribution of x bar is normal theta 1. So I take delta naught x to be x bar. So what I have to make sure? I have to make sure that it is invariant and a function of a complete sufficient statistic. So to show that it is invariant, what I have to see is delta naught of x1 plus c, xn plus c. This is nothing but mean of this. Mean of this means sum of all the components divided by n. So summation I is equal to 1 to n xi plus c by n. which is nothing but c is getting added n times, so it will become nc, and n will get cancelled, so plus c will come outside, and summation xi by n is x bar plus c, which is nothing but delta naught of x plus c. So it is invariant, and a function of complete sufficient statistic. So what is MRE? So C star minimizes, so what I have to show is expected value of, I have to look at C star, which is the minimum of, which is the minimizer of W of delta naught x minus C, that means x bar minus C whole square. So that is what my psi C is. So what is C star? I know that mean square deviation is minimized at expected value, so C star would be nothing but expected value of theta is equal to 0 at x bar. What is expected value of x bar when theta is 0? It is 0, because it's mean. Expected value of x bar is same as mean, but mean is given to be 0, so this is same as 0. So what is MRI? It's just x bar. And of course, just to make sure that you have not made any calculation mistakes, your MRI under square error loss function should be unbiased, and you know that expected value of x bar is theta, so it is unbiased. Of course, very straightforward application. You could have used the formula for MRI under square error loss function, which we did under that theorem. This is same as minus infinity to infinity t, density of at the point x1 minus t, x2 minus t, xn minus t. So that is same as product I is equal to 1 to n phi of xi minus t dt. This is the formula which we had done. This phi is the PDF of standard normal divided by minus infinity to infinity product I is equal to 1 to n phi of xi minus t dt. So this is a joint PDF of x1, x2, x. This is the formula which we did. If you want, if you calculate this, this will turn out to be x bar. So let me just stop over here today. You can try to do some of these assignment problems. We can discuss it in one of the tutorials. So try to look at various location models and try to find out what are the minimum risk invariant estimators in those situations. I'll put up one assignment on the course web page. You can look at those assignment problems. So this is all for today. Meet next time. Thank you very much.